So as usual, just take a moment to center yourself before we start with the next bit of maths. So now that we have a working definition of a set, and we know some examples of things that are sets and aren't, we're going to develop the notation that's going to help us communicate ideas about sets, so the mathematical notation that we need. So the first sort of notation that we use is called roster notation, and it really involves just listing the elements of a set and then enclosing that list in curly brackets so that we know that we're defining this as a set. For example, the set of primary colors, if you're writing it in roster notation, would be written open curly bracket, blue, red, yellow, close curly bracket. Now, one of the things you'll notice is that in our definition we didn't say anything about ordering of elements in a set, and that's because there's no ordering for sets. So we could equally well have written the same set as red, blue, yellow, or any other ordering. And those two sets are equal because we don't worry about the order, we're just thinking about are the elements in the two sets the same. Just to be clear, sets don't have to contain the same type of object. So for example, we could have a set that consists of the word cat and the numbers 1, 4, and pi. Not sure why we'd want that, but we could have it if we did. And then just to be absolutely clear, there's a big difference between a 3 just written like this, which is a number, and a 3 enclosed in curly black brackets like this. This is a set, and it happens to contain the number 3. There are two different objects. One is a number, the other is a set. So if we're thinking about the kinds of things that sets can contain, sets can include other sets. So we've seen the set that contains 3. But we could equally well have the set that contains the set that contains 3, which looks like this, 2 lots of curly brackets. So let's just take a moment to check that we understand what's going on here. I'm going to ask the question, is this funny thing over here a set? So remember our definition of a set says it's a collection of objects. It has to be well defined and the objects have to be distinct. Well, this is a collection of objects. Oops, it looks like we've lost a square bracket, curly bracket there. It is a collection of objects. We've got a number, and we've got a set, and we've got a set that contains a set. And now we have to decide, is it well defined, and are the objects distinct? So let's think about well defined. Well, if we look at the items in our collection, if you are a 3, or you're a set that contains 3, or you're the set that contains the set that contains 3, then you live in our set. If you're anything else, you don't live in the set. So this is very well defined. You can say whether an object lives in the set or not. And if we have a look, as we've already mentioned, each of those 3 objects is distinct. Although they look similar, they're really quite different. So these are each distinct. And so this funny looking thing is in fact a set. So you'll have already noticed it's got a bit tedious describing each set repeatedly. So often when we're working with a set for any length of time, we give it a name in the form of a capital letter. For example, you might call the set of binary digits B, in which case we would write B is equal to 0, 1. Didn't have to be B, but B for binary kind of will help remind us what we were talking about. We also need to be able to talk about individual elements and whether or not they're an element of a set. If X is an element of some set A, then we use the notation X and this funny looking E thing, A, and that's read X is an element of A. And sometimes we want to be able to say that something doesn't belong to a set. and we use sensible notation. So if x is not an element of A, then we say x, funny E thing with a line through it, A, and this is x is not an element of A. So if we have the set B of binary digits that we've seen before, then we would have, for example, that 1 is an element of B, but 42 is not an element of B. And if we've named our funny set of 3's and sets containing 3's as M, then we have, for example, the set containing 3 is an element of M, but the set containing the set containing the set containing 3 is not an element of M. Okay, so that should be quite straightforward. Now sometimes we've got a set that has a lot of elements and we don't want to write them all out in roster notation, but it's clear what they are because the elements form a pattern. And in this case we use 3 dots to indicate the unlisted elements, and these 3 dots are called an ellipsis. So for example, we could write the set of integers from 1 to 100 as 1, 2, 3, so that sets the pattern for us, and then 3 dots saying keep on going with the same pattern, i.e. increasing by 1 whole number, and then we end up with 1000, which says until you get to 1000, in which case stop. So this is pretty useful. Writing out 1000 would be very annoying. We can also use an ellipsis in 2 other situations. So sometimes we want to indicate that the list carries on in a particular pattern infinitely. So for example, if we wanted to list the positive integers, we could say, okay, well the pattern is 1, 2, 3, so take whatever you've got, increase by 1, and then just keep going, and there is no place to stop. Just keep going infinitely. We can also use the ellipsis if we're going in the opposite direction. So for example, the negative integers, we would say, well, you're going to be coming from negative infinity, and the pattern that you want is you would have -3, -2, -1. And in fact, you could combine these two to talk about all integers. And again, you're going to want to have the pattern at some point. So I'm going to put in a lot of elements here. -3, -2, -1, 0, 1, 2, 3. And you want to keep going following this pattern in both directions. Technically speaking here, you wouldn't need to put in all these examples, but sometimes it's just helpful. So that was one of the ways we use an ellipsis, as well as the previous one seen. And secondly, sometimes we want to list the elements in a more general set. So for example, if I want to list all the integers between 42 and some unknown integer n, then I would write 42, and this usually implies just keep increasing by 1 until you get to n. There's no fixed rule here, so if you wanted to make sure that people knew what the pattern is, you could have also written this as 42, 43, 44. Keep going with that pattern until you get to n. And this allows you to write a general set where you might want to talk about cases where n changes. So that's 3 cases where we use an ellipsis, and you should practice making sure you're comfortable with that. So we have some sets of numbers that we use so often in mathematics that we just give them a universally used standard symbol, and you'll have seen some of these. So the natural numbers we indicate with this funny calligraphic n. Integers is indicated with a calligraphic z. Rational numbers with a calligraphic q. real numbers, calligraphic R, and the complex numbers with a calligraphic C. And those are used worldwide, so wherever you go, they mean the same thing. In this course, we're also going to talk about the positive integers a lot as an example, so we're going to use this calligraphic P to represent the positive integers. This is not standard. Some mathematicians use the integer symbol with a little plus up top, and there are other symbols used. So the ones on the previous slide used everywhere, these are not standard. So roster notation is pretty useful, especially when we've got ellipses, but sometimes we want to be able to talk about the elements of a set based on their properties. And in this case, we use set builder notation rather than roster notation. So the basic idea for set builder notation is you still enclose your set in curly brackets. And then it has two parts. The first part is basically defining your variable name. So it's going to say, I'm calling my elements X. And then you put two dots, and this is sometimes also written as just a straight line. And then you have a list of one or more properties that X has to satisfy in order to belong to the set. This is much clearer if we look at an example. So for example, we might have the set of all X, where X is an element of natural numbers and X is less than 5. So notice we've packed a whole lot of English into some very straightforward mathematics. So this, I'm just going to write it out again, is read as the set of all X such that, so this is read as such that X is an element of the natural numbers and X is less than 5. And if we think about what that set actually contains, well, we could actually have easily written that using roster notation. If it's going to be a natural number and less than 5, that's going to be 1, 2, 3, and 4. Let's have a look at another example. So here we have the set of all X, where X is an element of real numbers and X squared minus 1 is equal to 0. So just take a moment to think about which elements actually live in that set. So we want real numbers, and we have to have real numbers such that when we square our real number and subtract 1, it gives us 0. And if we think about factorizing this, x minus 1, x plus 1 equals 0. So the only actual elements of this set would be minus 1 and 1. There's no set way of writing things using set builder notation. So I could equally well have written this set as follows. I'm creating the set of all x that are real numbers such that x squared minus 1 is equal to 0. And that would be equally correct. So you don't have to put the x element of real numbers after the colon, you could also put it before. And there are other ways to write. The basic idea is to try and make your notation as clear as possible. So let's look at one final example. We can use set builder notation to describe the rational numbers in terms of the integers. And notice here we're going to say the rational numbers is the set of all fractions of the form a over b, where our a and our b live in z and our b is not equal to 0. So you'll notice this shows how very compact set builder notation can be, but it also takes a little while to unpack. So let's just clarify what's going on here. So we've got a over b. So this is saying fractions of the form a over b. And then we have our two dots, which is saying such that. And then we say a comma b, and this means a and b are an element of z. You could have written this as a is an element of z and b is an element of z if you wanted to just make it absolutely clear. And then the final thing we have is that we also have a condition on b. It's not just an integer, it's that b is non-zero. So it's worthwhile spending a little time translating things written in set builder notation into English and vice versa.